Hello folks, I'm John MacDonald from Linear Photonics. Thanks for tuning in. I want to share with you the experiment we're setting up to try to prove Einstein's general theory of relativity during the total eclipse on August 21st. We've traveled out to Casper, Wyoming, in the foothills of the Rocky Mountains, which you can see in the distance here. We hope the weather supports our event. Right now the forecast looks pretty good. As I mentioned, we are planning to repeat Arthur Eddington's experiment, originally conducted in 1919, which proved Einstein's general theory of relativity. I'll explain how a total eclipse can allow us to perform this experiment in a minute. But first, let me introduce the rest of our team. In addition to myself, we have, on the right, Mr. Peter Kratz of Oceanside, California. His day job is Director of Practices for a major IT consulting firm. Pete is the astronomer on this project. Those are two of his awesome telescopes, flown in from California especially for this event. In the middle, Mr. David Catapano from Langhorne, PA, is the Senior Vice President of Engineering at Triveni Digital Corp., based in Princeton, New Jersey. Dave's role is to assist with networking our base station equipment and camera automation control systems. On the left is Mr. Jim Marr from Syracuse, New York. During the day, Jim is an aerospace engineer. On this trip, he is our analyst, developing and programming the sophisticated mathematical algorithms required to translate a picture of the eclipse to a proof of Einstein's theory. Here are some of our helpers. What's your name?
Grayson.
Hi, Grayson. That's Colton. What's your name?
Say hi, Lindley.
Her name is Shy.
She's shy.
Here is some of the sophisticated equipment we'll be using for this event. These two telescopes will be used to capture the images. Both are equipped with high-resolution, state-of-the-art CMOS cameras. We only have about 2.5 minutes of totality here, so those live video images need to be streamed to our base station, which houses our main computer storage and processing equipment. To do that, we will be using Linear Photonics fiber optic links. In addition, we plan to live stream the entire eclipse on a third telescope camera, which is directly connected to the internet. We invite you to watch on August 21st at approximately 10:15 Mountain Daylight Time as we video capture and live stream the entire event. I will point out that our ability to live stream will depend upon both the weather and the uplink bandwidth available in Casper, Wyoming. Generally, about 50 million people will be packed into a 70-mile strip of land in North America during this event, and bandwidth may become problematic. We simply can't predict. So if you tune in on August 21st, you may see still images. No reason to fret though. We will be recording the entire event, and we will post it later in the day if necessary. Go to linphotonics.com for a link to the video site. So about that whole Einstein general relativity thing. Here's what we're doing. Newtonian, or classical mechanics, predicts that light will bend around a massive object, like the sun. The bending is due to the gravitational field of the massive body. Einstein realized that, in addition to the gravitational effect on acceleration, space itself is actually bending, kind of like placing a bowling ball on a rubber sheet, except in 3 dimensions. Einstein's calculations predicted that this would cause twice the amount of deflection as predicted by Newton. If you're looking at the star, a distant star, it will appear to move away from the sun. This theory of Einstein was proved in 1919 when Eddington did his first experiment. It's since been proven many times using different techniques. We are attempting to recreate Eddington's experiment by taking photos of a star field during a total eclipse. For example, let's say this is a star field. There's no sun in that image. Those stars are in a fixed location. If the sun is in the image, those stars appear to move away from the sun. Their apparent position has changed. So how are we doing it? Well, we already took photos of the star field a couple of months ago. We have these as reference images. We also know fairly accurately where each star is supposed to be based on extensive databases collected by humans over the millennia. We also have awesome equipment as compared to Eddington's. So it should be easy, right? Ideally, we'd take 2 pictures of the exact same star field, exactly 6 months apart, so that one of the pictures would be at night because the Earth moved back around. We don't have the time or space for that. We have to compare two pictures taken at different times from different spots on the Earth, from different positions in the cosmos. If we could, we would take a picture on August 21st at noon and take another picture on February 20th at midnight of the exact same star field. We don't have that luxury. So here's what we're faced with. We need to correct the image in order to position it properly. The correction involves several factors. Some of these are rotation due to our location on the planet with respect to the star field, conversion to a celestial centered coordinate system which locates the stars on the celestial sphere, sometimes referred to as right ascension and declination. We have to identify the location of each star of interest from its smeared image using a mathematical technique known as a centroid. We have to correct for zoom differences. We have to correct for precession. We have to correct for refraction of the light through the Earth's atmosphere. Refraction causes the stars to appear higher in the sky than they actually are, depending upon how high up you look. The error decreases as your azimuth increases. We're going to use a least squares estimator to locate the entire star field according to the known locations. We're looking for a deflection of at most 1.7 arc seconds. That is a fraction of the width of a human hair held at arm's length. We'll be doing all of this with software routines we've already written. If all goes well, we'll be done number crunching before the sun sets for the second time on August 21st. So thanks for watching our little video, folks. Make sure you check back on August 21st to watch the live stream of the eclipse. Go to linephotonics.com for more details.